There's never been a mission quite like Stardust. This is the first time that we've gone out, collected the current stream of interstellar grains and brought them back into our laboratories. We've identified interstellar grains before in primitive meteorites. We've got this sort of tantalizing glimpse of those interstellar grains that came into our solar system 4.5 billion years ago. But these are the interstellar grains which are coming into our solar system now, and it's probably perhaps a different source of interstellar grains. So we're learning a lot more about the diversity of the interstellar sources for our solar system. Stardust was launched in 1999. So on 2 occasions on the journey, the aerogel collector was exposed to the interstellar medium, or rather the grains which have entered into the solar system from the interstellar medium.
And when you say interstellar medium, what do you mean?
There are many grains streaming onto the plane of the solar system which form completely outside our stellar system. So in other words, which aren't really related to the formation of our sun and the planets and the asteroids. They predate it, and they're brought from somewhere else, from other star-forming events.
How did you get this dust from space and then bring it all the way back to Earth? It seems like quite an impressive feat.
Yes, it was. Well, firstly, aerogel was chosen as the collector. It's very low density sort of silica sort of gel. So if you can imagine a tennis racket of aerogel tiles held together by aluminium foil, opening up on the Stardust craft on 2 occasions, came back in 2006, landed in the Utah desert with a parachute. So then it was put into a clean room and the spacecraft was opened up. Well, firstly to establish if we'd collected any interstellar grains. Because it's translucent, we can see where the grain is. From looking through thousands of high-resolution images, we identified a relatively small number of tracks which were caused by interstellar grains. And the other way, of course, of collecting was with the little impact craters on the foil due to the hypervelocity impact of the interstellar grains. So in the base of these impact craters, and we're talking a millionth of a meter across, there was a little bit of residue of the interstellar grain. By analysing that residue, that's another way that we can determine these interstellar chemical signatures.
How could you tell that they weren't from our solar system rather than another solar system?
For one thing, the angle at which the tracks had entered the aerogel. So interstellar grains have come from outside the plane of the solar system. So that means the angle at which the tracks hit the surface is quite distinct. We know the angle of the tracks, we know the composition, so we know it's not part of the spacecraft itself. So when we put all those 2 together and can compare them to astronomical observations, we are confident beyond reasonable doubt that these are grains from beyond our solar system.
So what can you tell about this other solar system from looking at these dust particles?
It won't just be necessarily one solar system. It will be a whole range of this constellation, an area in the night sky that has different sort of sources, different suns and different dust clouds.
Do we know how different it is from where we sit?
In the solar system, all the rocks and minerals that we see around us on Earth have been processed, melted, eroded, erupted in volcanoes, deposited in oceans. So the stardust of the solar system has been obliterated almost entirely because of the formation of the Earth. And now we're going out away from the terrestrial planets to collect them. So that was the real importance of Stardust, to collect this most ancient building blocks of solar systems, including ours, to find out what they're made of. So it's telling us about times and places completely away from our own solar system and before our sun formed. We're looking back into the past beyond our solar system when we study interstellar grains like this.
What are these particles actually made of? What's in them? What minerals are they?
Well, we're finding a range of different minerals. So, for instance, particularly we're finding iron-bearing phases, including sulfide. So when you see pictures of asteroids, that's basically this sort of stony meteorite material. But we're now finding a much greater range of compositions, including for the first time sulfide. perhaps the story coming out of Stardust, what we're learning is that there is a greater diversity of these compositions in the interstellar medium than we realised.